sections 1 through 3, we approximated definite integrals, and the formulas we use could have been, and sometimes were, derived by approximating f by a polynomial, interpolating polynomial, Lagrange polynomial, and integrating the polynomial, because polynomials are easy to integrate and differentiate. So, for example, Simpson's rule is often derived by approximating your function by a polynomial degree 2 that interpolates at the left point, right point, and the midpoint, and integrating the polynomial, and you'll get Simpson's rule. But we actually found it easier to not only test quadrature rules but derive them by using the theorem, the most important thing in the first 3 sections, the theorem that says that if a quadrature rule is exact for all polynomials degree m, if it's degree of precision m, then it's order h to the m plus 1. So you could derive Simpson's rule, for example, by saying let's just let the weights be a, b, c, and try to choose a, b, c so that it's exact for 1x, x squared, and you get 3 equations, 3 unknowns, and you get the right answer. And that's usually a little easier, and it tells you what the order is of the error also. Well, in this section 4, we're going to approximate derivatives instead of integrals. And again, we could approximate the function we're trying to differentiate by a polynomial and differentiate the polynomial, and that's easy enough to do. But it's even easier to use Taylor series expansions, not only to test our methods, but to derive them, as we'll see. So in this section, there's 3 most important formulas are 2 approximations for the first derivative and 1 for the second derivative. Most differential equations, for example, involve only first and second derivatives, so those are the most important ones. Sometimes they're higher third or fourth derivatives, but usually just first or second. So how to approximate first and second derivatives is important. And we have 2 formulas for approximating the first derivative. This one is just the Euler's formula, u of t plus h minus u of t over h. In fact, if you take the definition of a derivative in Calculus 1 is the limit of this as h goes to 0. So the smaller h is, the closer this is to u prime. So in calculus, you take limits to define integrals and derivatives. And here we just say, take a small h. So we want to see how accurate this is. Obviously, if h is small, this is an approximation to u prime. But we do that by Taylor series expansion. Expand u of t plus h as u at t plus h u prime at t plus h squared u double prime at t over 2 plus higher order terms. And notice I don't bother writing off t. If I don't say where these functions are evaluated, they're all at t. In fact, that's the whole point of the Taylor series expansion. So I've got apples minus oranges. I convert my apples to oranges so I can add them. They're all at t here. I just don't bother writing it. Okay, so now I've got the u's cancel, and I get h u prime plus h squared u double prime over 2 plus higher order terms divided by h. Divide out the h, and I get u prime of t. Now I put the t back in here. Plus h squared over h is h over 2 times u double prime plus higher order terms. That means the next terms are like h squared and so forth. So when h is small, they're negligible. When h is small, this goes to 0, but the other terms go to 0 even faster. So this is approximately the error. In fact, you can say the error is exactly equal to h u double prime at some point if you use the Taylor series with the remainder. Anyway, the point is it's order h. The error is proportional to h, which means if you cut h by a factor of 2, the error should go down by a factor of 2. If you cut it by 10, error should go down by a factor of 10. That's not very accurate. That's kind of the least accurate formula. So we want a little more accurate formula to approximate the first derivative. Let's try u at t plus h minus u at t minus h over 2h. That's the slope of the line connecting u at these 2 points, t plus h and t minus h, because this is t plus h minus t minus h. And now we expand u at t plus h the same as before, except we add one more term. Now u at t minus h, this is the same as u at t plus h, except replace h by minus h, and that makes the odd terms negative, the even terms stay positive. Minus h quantity squared is the same as h squared, minus h cubed is minus h cubed. So Here's u at t plus h, here's u at t minus h. We subtract them. The u's cancel. In fact, all the even terms cancel. The odd terms add, because hu prime plus hu prime, we get 2hu prime. And we get h cubed u triple prime over 6 plus another one, so we got 2h cubed u triple prime over 6, all divided by 2h. Cancel the 2h, we get u prime, and now put the t back in, plus h squared u triple prime over 6. So this is the error, and now it's order h squared, which is a lot more accurate. Now if you cut h by a factor of 10, the error should go down by a factor of 10 squared, 100. Now the third important formula in this section is approximating the second derivative, and this is the formula that's nearly always used to approximate second derivatives. U at t plus h minus u 2u of t plus u of t minus h, and we expand u of t plus h the same as we did before, except one more term. U at t minus h the same, one more term, and now the as before, the odd terms are negative, the even terms are still positive. And we got a u plus u minus 2u, so the u's all cancel. And now the odd terms cancel because hu prime minus hu prime cubed terms cancel. The even terms add, so now I've got 2 h squared u double prime over 2, and I've got 2h to the fourth u fourth derivative over 24. And now I divide through by h squared, and I get u double prime at t plus h squared u fourth derivative over 12. So that is the error in this approximation to the second derivative, because it's equal to the second derivative at t plus, that must be the error. So it's order h squared. So the last two formulas are both order h squared. They're more accurate than the first formula. So two ways to approximate the first derivative, one way to approximate the second derivative. Those are the most commonly used formulas. We can also use the Taylor series to derive approximations to derivatives, just like we used the theorem in the first three sections to derive quadrature methods. Basically, you just, if you don't know weights, you give them letters and you keep going until you determine what they need to be and make it exact for as high degree polynomials as possible. Well, here, do the same thing. For example, where did that formula that we just showed for the approximating the second derivative, where did that come from? The f of t plus h minus 2f of t plus f of t minus h over h squared. Where did that come from? Well, you can just say, well, let's try to find a, b, and c that make this an approximation to the second derivative, and use Taylor series to calculate the error. And then at the point where you get to the error, you say, well, what can a, b, and c be to make this error as high order as possible? So just carry the a, b, c along and expand f of t plus h and f of t minus h the same as I did. By the way, students always ask, well, how do you know how many terms to carry along? Well, I always say the answer is you don't know until it's too late. Notice I added more terms to that last formula. That's because I knew I needed it, but how do you know you need it? Well, you don't until it's too late, basically, until you see what cancels. So it's better to have too many terms than too few. You can always throw away the extra terms. If you have too few, then you have to go back and add terms, so it's better to have too many than too few. So, well, it turns out that they know that this is far enough. The h to the fourth terms is going to be far enough. How did they know that? Well, they tried it and it didn't work, so they added another term, whatever. Anyway, this is just the same formula. I called it u, but f of t plus h. This is f of t minus h. It's the same except the odd terms are negative. And so you take a times this plus b times f plus c times that, put it all together. You know, what we did a minute ago, I knew what a, b, and c were, and so I just calculated it, and this turned out to be 0 and so forth, and that turned out to be 0, but you don't know that now, so you just carry this along, and you say, okay, then if this formula here, now that I expand this into Taylor series and this into Taylor series, put it all together, put this all together, and I get this. Well, remember, we're trying to approximate the second derivative, so we want the coefficient of f to be 0, we want the coefficient of f prime to be 0, we want the coefficient of f double prime to be 1, because we're trying to approximate f double prime. If we were trying to approximate f prime, we'd want this to be 1 and that to be 0. So we need this to be 0, that to be 0, and that to be 1. And then we'd like for, as many terms as possible after that to be 0 to make it as high order as possible. But since we've only got 3 parameters to play with, a, b, c, that should be enough 3 equations. So we set this to 0, that to 0, and h squared over 2 times a plus c equal to 1. And then we may hope that that's 0 also. So that's what I was saying. The coefficient of f has to be 0, coefficient of f prime has to be 0, coefficient of f double prime has to be 0. There's your 3 equations for 3 unknowns. You solve it, and you find that b is minus 2 over h squared, a and c are 1 over h squared, which gives us exactly this formula. And now you can go back and figure out what the error is. So there's only the one set of values for a, b, and c that'll make this 0, and that 1. But it so happens that a equals c, so this, by luck, is also 0. This is not 0, but you can figure out what a plus c is, and that's the error. That's the first term in the error. So you get that for the error, which is the same as what we got. Okay, now let's do a little experiment. We use that second formula for approximating the first derivative applied to f of x equals sine of x at x equals 1. So we approximate the derivative of sine of x as sine of x plus h minus sine of x minus h over 2h. And the error should be order h squared, which means, see, I'm going to cut h by a factor of 10 each time through the loop here. I'll try h equal to 0.1 and then 0.01, 0.001, and it should get more and more accurate. In fact, it should, the error, every time I cut h by a factor of 10, the error should go down by 100 because it's second order. And here's the error. It's this approximation minus the true derivative of sine, of course, is cosine, and it's at x equal to 1. So let's try running this. And it's, let's go up to the top. It's beginning here. So when h is 0.1, we get an error of 9 times 10 to the minus 4. Cut h by a factor of 10, the error goes down almost exactly by a factor of 100, just down to 9 times 10 to the minus 6, so everything's going according to plan. Cut h by another factor of 10, the error goes down by another factor of 100. And another factor of 100, and not quite a factor of 100. And now we decrease h by another factor of 10, and the error actually goes up slightly. And keep decreasing h, and the error keeps going up. It's getting worse. By the time we get h down to, let's see, 10 to the minus 12, we get an error of 10 to the minus 5, which is much, much worse than what we got with whatever it was, h 10 to the minus 6 or so. So everything goes according to the theory until h gets real small, and then something terribly wrong here. Well, it must be round-off error. The theory that there's remember, there's 2 types of error in numerical analysis. There's the truncation error that has nothing to do with the computer precision. That's just the mathematical error. And the mathematical error should be order proportional to h squared, should keep going down as h goes down. But that isn't happening after a certain point because of round-off error. And remember in chapter 2, we said the main cause of, the only cause of serious round-off error is subtracting 2 nearly equal things. Well, that's exactly what we're doing here. See, when h is real small, we got sine of x minus sine of x, almost. So you're subtracting 2 nearly equal things, and the smaller h is, the more nearly equal they are. And so even though the truncation error is getting better and better as h goes down, the round-off error is getting worse and worse, and eventually it dominates. So approximating derivatives is just an inherently round-off error-prone problem. Approximating definite integrals is not, because you're basically adding areas, so you're not subtracting nearly equal things. But when you approximate derivatives, and second derivatives even worse, you're always subtracting nearly equal things. There's no way to avoid it. So the trick is you just have to make h small enough to make the truncation error small without making it so small that round-off error becomes a problem. So that's a little tricky. You can't make h real small. Okay, let's just look at one typical test problem for section 5.4. You're trying to approximate the first derivative using values of u at t, t minus h, and t minus 2h. So it's not symmetric around t, but nevertheless, choose A, B, and C, which make this as accurate as possible. Well, you just use Taylor series, whether you know A, B, and C or you don't. It's the same procedure. You expand u at t minus h, expand u at t minus 2h, which is the same as h, except replace h by 2h. And both of them, the odd terms are negative, the even terms are positive. Then you take a times u at t plus b times u at t minus h plus c times u at t minus 2h, put them all together, and remember you're trying to make this equal to the first derivative, which means you want the coefficient of u to be 0. You've got three coefficients, so you should be able to satisfy three equations. So let's try to make this 0 and the second derivative term 0, because we're trying to approximate the first derivative. And we want minus b minus 2c to be 1, because, see, the h's cancel. So if minus b minus 2c is 1, and a plus b plus c is 0, and b plus 4c is 0, that gives us three equations, three unknowns. We solve them, and that's the choice of a, b, and c, which makes it as good approximation to u prime as possible. If we were trying to approximate u double prime, we'd set this to 0, that to 0, and this, well, all of this divided by h equal to 1, but we weren't. Now, what is the order? Well, if you want to know the actual order of that's the best choice of A, B, and C. If you want to know what the order is, you're going to need to add a couple more terms and see what the next term is. Okay, one more old test problem. This is, I said we're mostly approximating first and second derivatives. With this problem, we're actually approximating the fourth derivative, and the formula is given, so it's not undetermined coefficients. The formula is given, and you just have to expand all of these in Taylor series. How many terms do you need? Well, you don't know until it's too late. I started to say I told them how many terms, but I guess I didn't, did I? I was mean. But so the basic formula you need to remember is u at t plus h. You don't need to remember all the others. You need to know that u at t plus h is u plus h, u prime plus h squared over 2, u double prime, etc. And then if you have a minus h, just change all your h's to minus h. If you have a 2h, change all your h's to 2h, and so forth. And this was all given, so I've saved the student a good bit of work in expanding. And well, in fact, I did. Okay, I did tell them how many terms, because I I wrote out how many terms. So you just have to take one of these minus 4 of these plus 6 of these minus 4 of these plus 1 of these, and divide by h to the fourth, and simplify, and it's a good mess, but it turns out to be u fourth derivative plus that, which is the error, order h squared. So you do actually have to approximate fourth derivatives sometimes, but not very often. But if you do, that's the formula nearly everybody uses.